Okay. So this is a slide deck that I never used before. I don't know how long it will take, so it will be something between 20 minutes and 2 hours. And let's see how that goes. But before I begin, that just one thing that I realized I missed in my slides in the previous talk is one way to use this result about differential privacy and generalization, which is there's a paradigm where you collect data and you do your research on, you split it in two parts. You do your research on one part of the data, you abuse it as much as you want, and you get some things that look interesting, and you rush to write a paper, but before you do that, you use the second part of the data to check that your results are actually meaningful. Okay, and because you haven't touched that second part of the data, the queries you're making on it are not adaptive, they are not tinted by the data. You can verify, if the sample is large enough, you can verify that with high probability your findings are correct, and only then you publish your paper. Okay? But suppose after using that second half of the data, the holdout, you're not satisfied. You see, you didn't get anything interesting, or you didn't validate that, you couldn't validate that your findings are correct. You go back to do your research and then have new findings, check them on the holdout. Then there is a risk, because this second time that you're checking your findings on the holdout, you may be adaptively, you may have some adaptivity here because you've continued your research after seeing results from the holdout, and this is a risk. But if you do your checking on the holdout with differential privacy, you don't have that risk. This is this immunity to this adaptivity helps you. So you can use the same holdout set, and as long as you don't exhaust your privacy budget, you're fine. And then either you use this technique where we said, you can make up to about n squared queries if you have n samples in the holdout, or if you use a technique like sparse vector that Katrina presented, was it yesterday or the day before? You can answer queries as long as you're not using your budget more than about n squared times. You can make more than n squared queries, but the bad ones, those where you cannot verify that the hypothesis is actually good, you can only make about n squared mistakes like that. And this is like a differentially private way to use the holdout. This appears in one of the papers that, I don't remember if it's in the references that are printed, but I think it's in the references that you will see in the online version of the talk. Okay. So that's for the generalization stuff, and we'll continue with something that is not totally unrelated, but no cows this time. We'll return to private learning in the sense very similar, in the sense that it's very similar to what Vitali was speaking about. So we care about the privacy of the contributors to the training set. And so let's see what we have there. Now, I'm not assuming, it may be a little, this talk will have concepts and notations from learning theory. I tried to minimize my use of notation, which means that I still use a lot of it. So I'll try to write some of these things on the board so you'll have them more accessible. I hope it won't be too difficult for those who are not familiar with these concepts from learning theory. But let's see how it goes. But do ask questions. So what is learning? No privacy yet. I'll abstract it this way. We have some underlying probability distribution or population. Think about it the way you want. We take a sample from that, we apply some computation, and why isn't this working? Oh, no, maybe I should stick this in. Oh, so here's the example. For instance, this could be the data that you collect. Maybe it's a bank, and it has the data collects includes a set of features like the percentage of down payment or whatever, whether this is this individual has a high debt and so on. And then maybe this is information that the bank collected for decisions about whether to give individuals, whether to grant them loans or not. And then in due time, they see if these people actually return the loan, and this indicates, so the bank can label each individual whether it was good risk or not. Okay, so that's a 1-bit label here for each of these individuals. So that could be our sample. And given this data, the bank is trying now to predict, and I want to emphasize that word, not to infer, and I liked very much the distinction that Vitaly made. To predict when a new customer comes, presumably another sample from the same distribution, whether this customer is good risk and hence should be granted the loan or not. Okay? So looking at this data, the bank could maybe deduce that what is written there is a good decision procedure, or maybe this thing, and so on. So let's do this again in a picture. So we'll assume that there is some distribution P over some domain. Okay? And then, as in the banking example, each point in this domain is labeled either 1 or 0, red or blue. Okay? We don't get to see all this picture here. This is just in the background. I just draw it for you. But we get to see samples from a sample from the distribution. And then we try to come up with some, so this is, maybe that was the entire domain and the labels. We only see a sample, and we try to come up with a function. I will call this function a hypothesis that tries to distinguish between those points that should be labeled red and the points that should be labeled blue. Okay? So what does it mean that this is a good hypothesis? So if we take a fresh point that we pick according to the same underlying distribution, we want that this point will be classified correctly. Okay? That's an example in this case. And what will require is that this will happen with high probability. It will be probability both over the randomness of the learner and the underlying, and the sampling from the underlying distribution. Okay? When we take a random point, it should be classified correctly, again with high probability. Okay, so keep this picture in mind, and let me write down some notation. So I'll copy this here so we have it in front of us. From talking about this previously, I think like notation and the concepts are really, if not, you're not used to it, it's sometimes hard to digest everything together. So I hope that at least having this in front of us will help. So we're going to have some domain of possible instances. And there's going to be a concept just a fancy name for a predicate. It's some function that takes a point in the domain and outputs either 0 or 1. Okay. A concept class is just a family of such objects. Okay. And for simplicity, only for this talk, we don't really need this assumption for a lot of the results that I will present. But for this talk and the next talk, we'll assume that we're working in what is called a realizable case or realizable setting, in which the labels for domain points for these instances are the correct labels are a result of applying some concept in the concept class, we'll call that the target concept, to the instances in the domain X. Okay? So there's going to be a distribution P. And then we'll speak about learning algorithms. The goal of the learning algorithm is to output a hypothesis, and a hypothesis is still just a fancy name for a predicate. Usually I'll call it H. And this hypothesis should be, in a sense, a good approximation for the target concept. And we'll define what good approximation is, but it will have to take into account the fact that there is this distribution P in the background. And it will be very natural to require that the output of a learner, because we know instances are labeled by some target concept in the set C, it will be natural to require that the output hypothesis will also come from the same class C. But sometimes we'll not require that, and if H can be outside, can come from outside C, we'll call that case, in that case we'll call the learner improper learner. Otherwise it's a proper learner. Okay? So the concept class is capital C. If we allow H not in C, then the learner is improper. Okay. So the model I'll work in is a model that is studied in by theorists mainly. It's the PPAC learning model of Valiant. This is the picture we've seen already. And first we'll define what it means for hypothesis C to approximate well a target concept C. For hypothesis H to approximate a target concept C. So we define this error, which is the probability that given a sample drawn according to the distribution P, H and C differ in the label they give to the sample point. Okay, I think that's pretty natural. So we're measuring errors, and we are weighting the errors according to the probability distribution P. Okay, and ideally, would like this learning algorithm to find H that is identical to C or has zero error, but this may be too much to ask for. Since error is something we cannot avoid here, because we're sampling from the probability distribution, and maybe we're that unlikely that our sample is not giving us enough information to actually determine to find a hypothesis that has zero error, or even a small error. Okay, so we'll have to take that into account. So we relax the requirement, and we'll relax it in two ways. One is that we will allow that H is approximately correct. Okay? That will be a good H. So we will have a parameter, I'll call it alpha, and this will be our bound on the error. So we don't require alpha to be 0 in general, and usually we won't. And furthermore, even that, we allow that in rare cases, even that will not happen. Maybe we will output a hypothesis that is totally bogus. Okay, so only typically we require that the outcome H would be approximately correct. Yeah.
So the learner outputs a function, it's not per input, the outputs H of X.
So the learner outputs a representation of a function or of a predicate. Exactly. Yeah. We're not. It's important that we're not labeling the sample. The sample is already labeled. We're getting a labeled sample, except for the special case that I will discuss at the end of the second part. The sample is going to be labeled. We don't need to relabel it usually. But what we're interested in is an ability to predict the label of new points. Okay? Exactly. The output of the learner is a like it's a, I don't know, a C code or like a representation of a hypothesis. Okay, other questions? And this typically and approximately are the reasons for this acronym PPAC. We want to be approximately correct, but we're only probably approximately correct. Okay? Most of the time we're approximately correct. So there are two notions of approximation here. So let me give you the formal definition. So here I just copied the definition of the error of hypothesis H. And we say that the learner L is alpha beta PPAC learner for concept class C if, and now we'll have universal quantification over the distributions and target concepts in this class in C. Okay, for all distributions P and for all target concepts little c in the class C. After receiving not too big sample, it can be a polynomial number of examples, and which are sampled IID from the underlying distribution, and each of them is labeled according to the target concept C. After seeing this, the learning algorithm crunches its input and outputs hypothesis H such that it has small error, less than alpha, with high probability, at least 1 minus beta. Okay? So a point I want to make clear is that we're not necessarily interested in, or we're not just interested in learning over the sample. Okay? First, the sample is given labeled, so that wouldn't be so helpful in many cases. But secondly, the fact that we manage to learn over the sample doesn't mean that we can predict. It doesn't directly mean we can predict. And we want to be able to predict the label of newly generated points according to the same distribution. Okay? So let's look at this. Suppose we're giving this thing, and the learner outputs hypothesis H that has small error when we test this hypothesis on the sample. Okay? So earlier I defined what the error with respect to the probability distribution P. Here it's defined with respect to the sample. I'll interpret that as if we're picking a random element of the sample and checking whether H is correct on this element. Okay? Suppose we manage to output hypothesis like that. Can we also say that the error on the underlying distribution is small? Okay? And generally, this is not the case because of what? What could we do with in this case? Overfit, exactly. So it may be that this H doesn't generalize. For instance, if we choose H to give the correct answer on all the points in the sample, but be random otherwise, then we're getting something that has error close to 1/2, but has zero error on the sample. So there is a difference between learning on the sample and learning on the distribution. That's a point to take from here. And you can generate many examples. That doesn't have to be the only example. That is, yeah.
When you're learning from the distribution, you're given a sample from the distribution.
Yeah.
If your H doesn't generalize, it doesn't generalize over doing the same thing. I don't understand.
I'm sorry, don't generalize.
Learning over a sample.
You're always given a sample. Yeah. The learner is given a sample, but your goal is not to learn over the sample, but to learn over the distribution. That's the point I want to make. Okay? So the fact that you managed to learn over the sample doesn't mean that you learned over the distribution. That's the point. Okay? Well, there's a reason we have this slide, because we'll have a similar slide later on when we'll speak about privacy. So we can ask many questions about PPAC learning. It's a rich area of research. And here are some important questions, or at least questions that I'll be interested in. First, you could ask, what is the sample complexity? How many samples do you need to take? How many examples do you need to take in order to learn successfully? Okay? Can you give upper bounds and lower bounds on the sample complexity for a concept class C? Similarly, you could ask about the time complexity. How hard is it to learn a concept class C? And because I mentioned improper learning here, you could ask whether there's any benefit in doing this very strange thing and choosing to output a hypothesis that is not contained in the concept class. Yep.
If you would have chosen H, which is the differential equation from S, then this promise would guarantee a good, back to the previous
Yeah.
So if your mechanism of choosing H would be differential divided from S, then this would be
So one thing you can infer from the previous talk is that if the learner is differentially private, then probably we're not going, there are subtleties, but probably we're not going to have this problem. Okay, if the parameters are set right, we'll not have this problem. So with differential privacy, essentially learning over the sample and learning over the distribution is the same thing. Yeah.
Just to be sure about a minor thing. So just let's say learning over sample does not imply learning over distribution. But the opposite is true though, right? Learning over, if I'm able to learn over distribution.
Not necessarily. You could be unlikely. Maybe there is a magical way to learn over the distribution, or maybe you're so lucky to learn over this distribution even when you got a very underrepresentative sample. Okay? Okay, so here's a motivating example for some of the problems that we look at today. Scurvy. It's a problem throughout human history, especially if you go out to sea for a long time and you don't get your vitamin C. And if you're a researcher, you may be interested in asking a question, how much vitamin C is needed to avoid scurvy? Okay, and how much vitamin C is enough is a threshold query. Like we're looking for a threshold function here. So we took samples from students and professors that participated in this research. You can guess who's who. And you see on the left we have those who have the lower vitamin C values. Some of them are, one of them at least is in this room, no? Where are you?
Understanding.
What's that? One of the students, I meant. And some of them had higher levels of vitamin C, and you also see the labels. And this is like a question of how, given this data, how would you predict what is the right level of vitamin C that is needed for avoiding scurvy? Okay. For instance, maybe this is an answer. Here. Maybe this is an answer, or maybe this is the right classifier, and so on. Okay, and here is the same thing in a less funny or more funny picture. And in this case, learning over the sample is really easy. You output any consistent hypothesis. Obviously, you can find one taken from the set of threshold functions, and the question whether this is good. Okay, so before we answer this question, let's do something even simpler. Okay, and suppose the class of concepts that we're interested in is this very simple class of point functions. These are functions that evaluate to 1 on just one point of the domain, and there are 0 elsewhere. Okay, really simple. And can you suggest a PPAC, a learner for points? So what is natural to do? Like you see a collection of points. Some of them are labeled 0, so some of them are labeled 1. Maybe you only see one kind of label. If you see the label 1, then that's conclusive. You know that that's the concept. If you don't see the label 1, what would you do? Maybe choose a random one. Why would that be enough? It's not generally enough, is it? Because maybe we haven't seen enough samples to actually, maybe there is weight more than alpha to samples that are labeled 1, but we didn't take enough samples, so we didn't see one, and we thought mistakenly that that these are really rare. So in order to make sure we don't make a mistake, we need to take enough samples here, and roughly 1 over alpha samples should suffice, because after 1 over alpha samples, you expect to see one, at least one that is labeled 1, if the weight of this point is at least alpha. Okay, and so this is the analysis. The probability that the weight of this point is more than alpha, but we completely miss it, is 1 minus alpha. If we take n samples, the probability that we miss that point is this thing, and this says that to miss it only with probability beta, it's enough to take n to be log 1 over beta over alpha. It's a very simple calculation. Okay, questions? Okay, this is not too fast, is it? Okay, good. And now we can generalize this, and there's a result that is called Occam's razor. Let's begin with the finite concept class. And we'll take a sample of n IID examples sampled from the underlying distribution. There's some target concept, so yi equals the application of that target concept on xi. And the algorithm is just going to choose a consistent hypothesis, the same way we did with the points and with the threshold. And we're guaranteed that this happens. We are in the realizable case, so we know that each point is labeled according to one of the concept class, the same concept class all over C. So there is a consistent hypothesis. We just pick one of the consistent hypotheses, and that's it. Okay. Now, if we take enough labeled samples, and this is a number like logarithmic in the concept class over alpha, and we output a consistent hypothesis, then this is going to be fine. And to see that, we're just going to use the bound that we used earlier. No, actually, yeah. So if the error is greater than alpha, then the probability that we are missing a point where H and C are inconsistent, each sample is such a point with probability 1 minus alpha. We repeat it n times, and that gives what we need. There are at most C minus 1, but I will write C here, bad concepts that could mislead us. And using the union bound, we get that taking this n should suffice. This bound on n should suffice. Okay? Is it? Give me a feedback whether, yeah.
So the learner should be efficient for many samples of consistent.
So if you, in the definition, I did not require the learner to be efficient. Usually you would, okay? But I just didn't want to get into efficiency questions here. But it's certainly a good question. Is it always easy to find a consistent H? And it may be that it's not. Yeah, sure. You can give examples where it will be NP hard to find a consistent H. Yeah. So let's go back to this example. Like, remember, we were trying to learn about scurvy. So here's a PPAC learner. We just need to apply this recipe that we just got. It requires only a constant number. Sorry, what is that? No, this is not what I intended to have here. Okay, we could apply the recipe, but then we would need how many examples, roughly? So there are T concepts in this concept class. We would need log T examples, but we actually, I want to say we can do better. I don't know why I have this slide here, but let me go over it. Anyways, here's a way to do this. Let's pick a consistent hypothesis this way. Let's I be the largest such that we see a sample labeled 1 with the x value being I, and we return that concept. It certainly is a consistent concept. And otherwise, we just maybe return the all zero function. Okay. So again, I don't know why I put this slide here. That's a mistake, but a similar analysis to what we did with the points would work here to show that the number of samples that are needed does not depend on T. This is why I mean by order of 1. It will depend on the parameters alpha and beta. So it will be something like log 1 of beta over alpha. Okay. Now, so as you can see, so we had this recipe here that works well as long as the concept class is finite, because otherwise you take the log and you get something too big. So it works as long as the concept class is final. It says that the most you need, the largest number of examples that you need is something like logarithmic in the size of the concept class, okay? And then we had the following example that showed that in this case, yeah, we could take log T samples, but we don't need to, okay? Just order of 1 samples is enough, okay? And you can generalize this. And this is another concept that Katrina mentioned, the VC dimension. Let me just go over this fast. If you are not familiar with the concept, I think it's a very interesting concept to study and to know about. But if you end up going through the next 2 slides and not getting it, that's fine. It's not going to be that important for the rest of the talk. Okay, so you can decide to take a break if you don't like this now. Okay. So this concept of VC dimension is a measure, in a sense, a measure of complexity, measure of complexity of a concept class. Okay, and it measures, in a sense, how concepts can vary on a collection of points. Okay, so given a collection of distinct points from the domain and a concept C, and usually this is written as a set, but I wanted to emphasize that we ordered them, so I put them as in a vector here, and they are distinct. And take the concept C, we can apply C to this collection, and this only means that we are labeling each of the points in the sequence. So we're getting a string of n bits here, okay? And similarly, we could do this by applying every concept in the concept class on the set S. So just to see that we follow give me a bound on the size of this set. How big can it be? How large can it be? Sorry? So it cannot be more than the size of C, that's correct. Can you give me a better bound? Or a different bound? Sorry? 2 to the n, exactly. It can be at most 2 to the n. And does it have to be 2 to the n? So if C is less than 2 to the n, then it would be less than 2 to the n, but it can also be less than C, okay? But at most 2 to the n. Okay, good. When this set is a full size, we say that it is shattered by the concept class, okay? Let's see an example. Suppose our domain is of the real numbers, and the concepts are like these things that functions that look like that, okay? So it goes up at the point A, then goes down at the point B. And let's pick a set 2 and 7. Let's see what kinds of labels we can get for this set. So if we, for instance, if we take this concept that goes up on 1 and down, on 0 and then down on 1, it labels both points 0, and so on. You can see, you can get the labeling 1, 0, 0, 1, and 1, 1. So we get that this set is shattered by the concept class in this case, okay? But if we will look at this, at any set that contains 3 distinct points, it cannot be shattered here because we'll not be able to, like if the points are ordered from left to right, we'll never get this labeling, okay? We'll get 1, 1, 1, but we'll not get 1, 0, 1. So with this concept class, there exists at least one set, actually many sets, that of size 2 that are shattered, but no set of size 3 is shattered, okay? And the VC dimension of a concept class is the size of the largest collection of points that can be shattered by this concept class. So in this case, we see that there is a collection of 2 points that is shattered, but no collection of 3 points is shattered, and hence the VC dimension is 2. Okay. Why is this an interesting thing to look at, you may ask? And the reason is that it's tightly tied with the sample complexity of PPAC learning. So let's begin with a concept class, and let's denote its VC dimension as D. We can show several things. For instance, if we have a collection of n distinct points, we know that the number of different labelings, I also used the term dichotomies, that we can have for the set S is bounded by, if n is less than D, then we get that we get all possible dichotomies, okay? So it's always less than or equal to 2 to the d, but we know that there exists a set that on which we'll actually get 2 to the d. Okay, and then one can prove the following theorem that bounds the size, the set of the dichotomies, and you see that roughly after we go, so it can grow exponentially until we get to the VC dimension, but then it only grows polynomially in the with the exponent being the VC dimension. And furthermore, one can show that if you have a concept class that has a finite VC dimension, then this can be used to bound the number of labeled examples that your learner needs to see. Okay, so you see that we get something that is linear in the VC dimension, and it depends on the other parameters. Okay, and if you have this number of labeled samples and you output a consistent hypothesis, then you're fine. Okay, and there's an almost matching lower bound. So the only difference is this factor of log 1 over alpha here. Okay, so let's see another example. And these 3 examples that I'm talking about, like the points, the thresholds, and the parity function, we'll look at them again soon when we'll speak about private learners. So we're still with classical non-private learners. Let's see how we can learn parity function. Here the concept, typical concept is this. R is a binary string of length d, okay, this R. And X is also a binary string of length d. And applying CR on X is exactly as computing the inner product of R and X modulo 2, okay? So that's a parity of the inner product of R and X. The physical dimension of this concept class is D, and let's see why. All I need to show, so it's only not more than D, because this concept class is of size 2 to the D. When we talk the logarithm, we get D. Okay, so I only need to show that there exists a set such that we can get all 2 to the D different labelings, all the dichotomies. So if we take this set to be the set of each of these is the basis vector in, this is like in the direction 1 up to direction D. Okay, so for any R in 0, 1, 2 to D, we're getting here, so this element is going, multiplying by E1 will give us the first bit of R, then multiplying by E2 will give us the second bit of R, and so on. So we're getting, when apply the concept on the set S, we're getting the string R. So we can go over all R this way, and we're getting all 2 to the D labelings, okay? So this suggests that we have a PPAC learner for parity with only order of these samples. And actually, this learner can be efficient because all we need to do is to solve a system of linear constraints, okay, to find a consistent solution. So each example is a linear constraint over the field GF2. For example, here, this means that R1 plus R2 plus R4 should be 1 modulo 1, okay? And we take this number of samples. I'm missing here the dependency on the alpha and beta parameters. And we get a system of linear equations. We solve it. One of the solutions, there must be a solution because we're in a realizable case. and one of the solutions, like any consistent solution, should be fine. Yeah.
This term is the one which was implied by the general theorem about the VC dimension, or is it just an example?
So it's implied by both, because the VC dimension and the log of...
This term is sort of the linear. I mean, it seems you have the general theorem for any.
So the general theorem doesn't say how you find a consistent hypothesis. Remember? It only says find one consistent hypothesis, and that should be fine. And here you have an efficient way to find a consistent hypothesis. Okay? So let's return to our problem. Do we have a privacy issue? And I think hopefully Vitaly convinced you to some extent that there could be a privacy issue here, that the hypothesis or model that we output could include information that about individuals in the data, or at least could allow deciding whether an individual contributed his data to the learning process or not. And look at this case. Suppose we use the learner that we described earlier that just picks the point, the rightmost point that is labeled 1, and outputs that as the hypothesis. But differential privacy is not preserved. For one technical reason, is that this is a deterministic algorithm. In your exercise sheet number 1, I think, there was a simple exercise to show that if an algorithm is deterministic, then unless it's totally useless, it's not differentially private. Okay? So this is not totally useless. It can give different outputs and different inputs. In deterministic, it cannot be differentially private. This is like one way to check this. But moreover, this algorithm probably shouldn't be called private in many reasonable senses, because it does reveal someone's data. Okay? And maybe if you have some external information, you could identify that person and actually learn that this data, in this case, belongs to Shiva. Okay? So it feels that there is something wrong here, not only just because we don't obey the definition of differential privacy, but inherently there is something non-private in this procedure. So although our goal in learning is not to learn about a specific individual, we are trying to learn about the distribution. So although privacy is not necessarily contradictory to this goal, the fact that we learn and produce a specific hypothesis doesn't mean that we still preserve privacy.
So what's the problem with the privacy of this person? I mean, what
So
does it tell you about it?
So you maybe like if first like suppose you know Shiva's vitamin C count, but you don't know whether he participated in this study. So that could tell you membership. But it doesn't have to be the only way his privacy would be breached. Maybe you have some external information. Maybe you know. Okay. Maybe you have some external information about this, and this allows you to learn more about him and so on. Okay, so in private learning, we will try to prevent this and other potential privacy breaches from happening by requiring that not only the learner is a good learner, but also that it preserves differential privacy with respect to its input. Okay? So let's begin with some intuition. So that was our data, and the learner produces some hypotheses. That's interesting. It's on quiet. And then, so actually the learner will have a distribution over hypotheses, and one of these is going to be picked in every execution. The distribution is determined by the input and the mechanism. And what we want is that if one, so it should be a PPAC learner first, like it should be useful, and also it should satisfy differential privacy in the sense that if one of the records is changed, maybe arbitrarily, now we're not talking about the case where this is taken from a distribution, but more generally, then the distribution over a hypothesis shouldn't change much. And these are two quite different kinds of requirements. The first one, learning is an average case guarantee. We assume that our input comes from an underlying distribution, and we only test the algorithm with respect to that underlying distribution, even if it's unknown. But that's how we define a good learner. When we speak about privacy, we don't want to make such assumptions. We want also to get privacy, even if our assumption that the input comes from an underlying distribution and that samples are taken IID, even if that assumption is incorrect. And we require that we achieve privacy, differential privacy, with respect to worst case input. So this is a worst case guarantee, okay? So and the difference is that we see all these probabilities over the input here, but in the definition of differential privacy, we have a for all quantifier. Okay, so let me just put forward the definition. Unfortunately, we have quite a few parameters. So the alpha and beta parameters come from the PPAC learner, and the epsilon and delta is those that hopefully by now you like and love, come from differential privacy. And we say that L is a PPAC learner, private PPAC learner for concept class C. If two things happen, one, it has to be a PPAC learner with the parameters alpha and beta. And the second requirement is that it's differentially private with the parameters epsilon and delta. So here we see our average case requirement, because here the probability is over the sample and over the algorithm. But here the probability is only over the randomness of the algorithm. Yeah.
Is it very unreasonable to define privacy with respect to distribution in this setting?
That's a very good question. I think security has to be taken in a more worst case fashion than utility. If not, then at least for the following reason. Suppose your assumption about the input is incorrect. Okay, suppose your input does not come, is not sampled IID from an underlying distribution. Okay, you performed your learning task. You learned the hypothesis H. You thought that it would be good, but because of your wrong assumptions, it's bad, it's crappy, okay? What happens? You could correct your assumptions and try to adjust the learner or your model and whatnot. Suppose you made an assumption, and based on that assumption, you thought you were getting privacy, but the assumption was incorrect. Information was leaked, and there's no way to take it back. Okay, so this iterative way of working is okay, I think, in most cases for utility, unless this causes, I don't know, a nuclear plant to blow up. But in many cases, it's reasonable to do something iterative here. Say, I'll make these assumptions. If it didn't work, I'll look more closely into my assumptions. I'll improve them. I'll redesign my algorithm. But here, if information was leaked, you just lost the game.
This is science, right? Science, you have a hypothesis, you get it wrong, you fix it.
Exactly. This is in life, this is science, this is how we work. And I think that's fine in most cases. With security games, I'm not sure. I think we have to be much more conservative. So you remember I had a similar slide about learning over the sample and over the distribution. And if we have a differentially private learner, and suppose we manage to learn over the sample, okay? You can ask, does this guarantee that the error over the distribution is small? And the answer is yes. And it will not, like, given the theorem I spoke about earlier, it will not grow by more than maybe epsilon plus delta if the sample complexity is at least this thing. Okay? So, in a sense, if the sample complexity is big enough, we can, in many cases, blur the differences between learning over the sample and learning over the distribution. And for the rest of the talk, I will do that. Although there are some subtleties, as I said, but they are not that important. Okay, let me check the time. Are we close to a break?
Supposed to be breaking up for 15 minutes, yeah.
Okay, so maybe this is a good time. Yeah, so it took more than 20 minutes. Good. So maybe this is a good time for a break, and then we'll continue from this point.